All right, guys, let's go over lesson 3.2.2 about residual plots. Please have your red pens out so you can add some notes as we go. All right, so in the last lesson, which hopefully you have done, if you have not, I would love for you to go back and do that. It talked about the least squares regression line a little bit. You can find this on your calculator. You also can find it from a computer output, and sometimes you can find it, you know, if it's a lesson, we can use one of the applets to find it. But the A is the predicted y-intercept, and the B is the predicted slope, and y hat is the predicted y. So really it's the, yeah, it's the predicted, this is the predicted y, and this is the predicted y-intercept, and this is the slope of the line. So when you first take a look at this, it does appear to be linear, I would say, like just kind of looking at the dots. There's some above, a little below, kind of follows a line. So maybe you said linear to start off with. When we're using the regression line to predict the stock price, we're basically just taking the equation here and plugging in some x values. So I did that with 2010 and got 7.54. And I found that the residual was negative 3.83. Okay, so just a note, I'm going to go up here. And I want to like show you what the residual looks like as best I can. So that line that I just drew at 2010, that is the negative 3.83. That's the distance from the prediction, which the prediction is the value on the line, to the actual point, which came from our table. So residual equals the actual value minus the predicted value. The order does matter. You want to make sure that the actual value goes first. And so I usually like remember it just with wrap. Like that's how I remember what order to do it in. I did a similar process for 2022 and got this. And then again, this was the actual price in 2022, and this is the predicted price. So that also was negative. Oh, hold on a moment. That doesn't seem right, does it? Oh, yeah. No, this is not a negative number. I just copied that wrong because it's obviously the actual is bigger. The way I kind of caught my mistake was I was looking at the graph and I noticed that if I actually drew the residual, it's above the line. It's right here. Okay. So now is a good moment to talk about something that I would love for you to jot down. It's like, why is this called the least squares regression line? So this one's a little, I'm going to try to draw the residuals for every single point. Obviously, some of them are like really close to the line. So I'm drawing vertical lines from the point to the prediction. At 2006, the line doesn't go down far enough. So there's the residual. I'm going to make a little note here that like the up and down line is the residual. And it turns out that the line that's going to be the line of best fit is the one that has the smallest square. The smallest sum of the squared residuals. I'm like not completely all better, guys. I'm feeling a little woozy, so trying to do my best here. So if I added up these residuals, some would be negative, some would be positive. A lot of them would kind of end up like canceling each other out. And so what the calculator does when it's doing this modeling is it actually finds the residuals, but then it squares them and then it adds them all together. So if you can imagine having a bunch of different lines that have the residuals figured out and then the squared residuals figured out, the line that has the smallest sum of the squared residuals is the least squares regression line. So you will hear me refer to that all the time as the LSRL. So it just gets old writing least squares regression line over and over again. But that's why it's called the least squares, because the sum of the squares is the least when it is the line of best fit. Okay, so going back to the actual problem. We're going to fill in the blanks for the ones that we calculated, which there was actually like an older version of this activity where you had to calculate all of these. It took a long time. So I like this one better where you're only calculating a couple of them. So on question number 2, we found that that was 7.54. And when we found the residual, we found that it was negative 3.86. And then here, this was 41.06, and the residual was positive 3.95. Okay, so what we're about to do is make a residual plot. Basically, we are just looking at the year and its residual. That's what we are graphing, is the year and its residual. Those middle columns were just so we could calculate the residual. You could see where they were coming from. Okay, so if I plot these points, it's going to look something like this. And this is, you know, I'm like touching my computer screen without a stylus. And so this is really, really approximate. But we have 6.48 and then we have 0.78, negative 3.86. It's supposed to be on 2010. We'll pretend that's on 2010. Negative 3.14. Negative 5.22, negative 0.37, negative 0.96, 1.25, and 3.95. Okay, this is not the best, and I kind of wish I had made the dots a little bit fatter. This is probably going to make it worse. It's hard to touch it exactly right. Okay, I think you get the idea though. There are all the points. So here's some red pen things that I would love for you to add. The points that are, since these are the residuals and 0 is here in the middle, the points that are up above the line is where the actual is greater than the predicted. And then the points below the line are where the predicted is greater than the actual. Or you could say actual is less than predicted. Okay. So question number 6, I have more to talk about that, but let's question number 6 goes with this actual and predicted thing, like comparing the two of them. So for which was it actually, what years was the actual stock price greater than predicted? That's those that are above the line. So that looks like 2006, 2008, 2020, and 2022. Okay, so that was the ones that were greater, and then the ones that were less were all the ones that were below the line. So that was 2010, 2012, 2014, 2016, 2018. Does the residual plot have a pattern, and what does this suggest about the linear model that we used for making predictions? Okay, so this is part of the issue, part of the whole lesson is like this point. There definitely is a pattern. Do y'all see it? Like the residual plot is actually curved, and that is not good. So I'm gonna write the residual plot has a curved pattern. The linear model might not be the best model. And here's some things I want to add in red. So when I said it had a curved pattern, it's because it went like plus, minus, plus. Okay, so if it's like spread a little more randomly, like that's actually good. That means a linear model is a good thing. But when it looks like this, positive, negative, positive, like that's not a good idea. So I kind of just wanted to add a little thing off to the side here. To say if the residual plot has no pattern, like it's random scatter, then the line is a good model. Okay. So something with a residual plot, that's what this is called. If the residual plot has a pattern, then a linear model is not the best. If it has no pattern, then the line is actually a good model. Okay, the big ideas are actually fairly simple today. One is the definition of the least squares regression line, which you do need to know and will be one of your note cards. The least squares regression line minimizes the sum of the squared residuals. So it is, and sometimes, like I can remember specifically the question last year, like the multiple choice question. And I feel like they don't have to necessarily use the term residuals. They could say like the distance between the actual stock price and the predicted stock price or something like that. Like they could put context in there instead of using the word residual. When you make a residual plot, it's good if there is like kind of random scatter. Like this has a lot of points on it. It's usually not quite that much, but it's good if it's kind of randomly scattered. That means a linear model is actually a good option. It's bad if there's a pattern like this or like this. And this one also is bad where it kind of starts off small and then it like spreads almost like a cone or something. I think that's called heteroscedasticity, which I think is just a really fun word. So pause the video here and copy down these big ideas in your notes, please. This is for section 3.2.2. And when you have it written down, I wanted to add something on the other page back here, I realized. So here, we kind of need to adjust our answer. It actually wasn't linear. It actually ended up being non-linear. And we saw that when we did the residual plot. So it actually is non-linear. Also, just because I was typing, I didn't have it on here, but it actually does matter. On 2 and 3, I should have put hats on these Y's because the hat is indicating the prediction that it's coming from the least squares regression line, not that it is the actual Y. So we use Y hat for predicted Y, and we use a Y for the actual Y. All right, I would love for you to attempt the check your understanding just to make sure that you are remembering how to do this, including reading this little printout over here. If you're looking at this printout and you're like, oh my gosh, I have no idea what that is, it's very likely that you didn't do yesterday's lesson. So you're going to need to go back and look at yesterday's notes. I posted a PDF of the filled out version of the notes. So you can tell like which one of these numbers is the A and which one of those numbers is the B when you are writing your equation. So one of these numbers is A and one of them is B. You need to look back at yesterday's lesson to figure that out, or you could also look in your textbook. I have posted the answers to the whole entire lesson in the folder for today, in the subplan directions. So I'd love for you to like check your understanding answers with that document when you are finished. Thanks, guys.